are in the everyday physical world, in front of the building that houses Sun Microsystems Laboratories, the home of the SELF project for the past 4.5 years. I wanted to start out here because physical objects are the fundamental metaphor upon which SELF objects are based. There are several important properties of physical objects that we tried to capture in the SELF system. One of them is directness. You go directly to an object to inspect it or change it in some way. We want that in our system. We also want a uniformity. No matter where you go out here, there's just more three-dimensional physical objects obeying the same simple fundamental laws. You get closer to them, they get bigger, they respond to contact forces, and so on. We'll want that kind of uniformity in the system as well. There's a third property that's kind of interesting and subtle. The physical world is continuously running. There's no run-edit mode. Let's consider an office in this building as a physical system. Someone can be in their office using it for their routine daily tasks, while others come in and make changes to it. Because there's no kind of run and edit distinction, both kinds of users can operate on the system at the same time. We'll want that same kind of lack of run-edit distinction in our system. It's not enforced by the underlying physics of the real world, and it offers a certain kind of liveness to the feel of the world, consequently. So these three properties, directness, uniformity, and the liveliness of feeling like you can make runs or edits without a strong distinction, are the properties we'll have in the SELF system. Let's go look at the SELF system now. There are a couple of independent ways in which the properties of the physical world are embodied in the system. Let's look first at the language semantics. This is a SELF object. A SELF object is simply a collection of slots. Each slot has a name and a reference to some other object. So this object here might represent a Cartesian point with x and y values referencing numbers. Numbers are first-class objects in SELF. Computation happens in the system through sending messages. I can send the message x, for example, to this object, and that will activate the contents of the x slot. An object simply returns itself when it's activated, unless it's a method object. We have a method object here in the length slot. Let me try to send the message length, and evaluates to this floating point number. What happens when a method is activated is the system makes a copy of it and installs it in the context of this object, so all the messages are then sent to the message receiver. All these tokens are messages, x and y, of course, square, plus, and square root. And the square root was returned as the result of the message send. Now, an object can respond to more than the messages that match its own slot names, thanks to inheritance. If a message name doesn't match locally within these slots, the system continues to look up through objects referenced by slots whose name end with an asterisk. These are called parent slots. So here you could see there are methods for doing arithmetic and printing and so on, and in fact there are further parents farther and farther up into the system. A parent is a natural place to store shared state and behavior. For example, the length method might be used by all sorts of points, so let's move it from here into the parent. But we would want each point to have its own private x and y slots. If I make a copy, the routine way to make new objects in SELF, it will have this parent in common, but its own private x and y slots. This is reminiscent of instances in classes in class-based systems, but in fact it's quite a bit more flexible than that, because, for example, I might decide that I don't want x to be a constant 43 in this case, but a method object. So let's change the x slot in this object from returning a constant to actually performing a computation by installing this method. Now the x slot will return the value of y. We've created a point whose x value is constrained to equal the y value. In fact, any object can be inherited from. Now this object inherits from our original point, and if I remove its y value, we'll have a point whose x is computed to equal y and whose y is inherited from this object, the value 1. For example, let's send it the message length again. And we get the square root of 2 as an answer. That's because when the length method runs, it asks for x and y, which are now both equal to 1, and returns the square root of the sum of their squares. The uniformity of Self's simple and tangible object model gives the system quite a bit of flexibility. We'll see how the same kind of physical properties are embodied in Self's user interface. The fundamental graphical object in Self is called a morph, from the Greek word for thing or form. Every morph can be picked up directly and moved around, or you can pop up a third button menu on it, and it has entries like dismiss or resize. We can build up more complex graphical structures through embedding. To embed one morph onto another, I simply drop it on and, from its third button menu, select Embed and Morph below. That makes them into one unified object. We can take these objects apart once embedded using a tool called the core sampler. The core sampler gives us a story spread out vertically for the depth below it. I can reach through that portal and yank out the pieces that way. One of the important blue button menu elements is called the outliner for the morph. This gives us the self-level story for that object. Here are all the slots. It's just like the one we saw just a moment ago, but it's got a little more decoration around it. In fact, the outliner is itself built out of this embedding mechanism. The whole interface is built in Self, so we can take it apart to arbitrary levels. You can see there's quite a bit of structure in this system. Let's look now at a much more common application. We'll look at an ideal gas simulation. An ideal gas simulation just consists of a gas tank here containing some green atoms that will bounce around. Let's use the core sampler to take this application apart. Let's look at one of these atoms in here. I could yank it out, and I'll ask for the outliner for it so I could see it as a self-level object. Here it is, a collection of slots. One of the slots is called raw color. It has a color object in it. And let's change this from being just a constant color of green to a color that's computed. I've got a method over here created in advance. The method simply will take the green color and the red color and interpolate between the two values depending on the energy of the object. In the Self environment, any bit of text can be evaluated at any time, so we could see what that object is, and we can in fact also turn it into a button for use in an interface if we wanted. Pressing the button can give me the result of that as well. So I'm going to redirect this slots pointer to point to this method object, and we should now have a object, an atom whose color will represent its energy. Let's make a copy of that and embed it into the gas tank and see if we can get its color to show itself here. I'll bang this around. Yeah, you can see it's getting red there as we give it a lot of energy. Now I might like this behavior for all atoms in the gas tank. So I can make the prototypical atom have this behavior. Let me get the prototypical atom, which is stored in a global namespace object. Now the global namespace is simply another self object with its own collection of slots. And here's the prototypical atom. I'm going to change its raw color slot from the stored value to the computed value. I'll bring that method over again and put in the computed value for color. So in this way we can affect now all future copies of the prototypical atom. And let's see if we can make a more complete interface to our gas tank in here now. I'll start by asking for this object's outliner. The outliner will let me see all the slots, of course. And in fact, I can use the outliner to send this object messages, like here's one that says add an atom, so I'm getting a copy of the prototypical atom and injecting it. Here's remove an atom, so we're taking it out. We can also turn any of these slots, sort of copy them out and make them into a button for use in the interface directly. So here I'm getting the remove an atom button, and that will still work, of course. And here's one, add an atom. Here's start and stop. See, when I add an atom and I press stop, the simulation stops running. And I may want to add one more button here, which I can get from the menu. By popping up the blue button menu, I can pin it down and then use a core sampler to extract any of the elements in the menu as a button. So here's the resize button. I might want to incorporate that into the interface. So I've been starting to build up an application here, but it's looking a little bit rough. I'd like these buttons to, of course, all be lined up. For that, I'm going to bring in what's called a row morph. A row morph simply takes the objects embedded into its surface and enforces the constraint that they line up. So let me grab all these buttons in one fell swoop and drop them on and embed them one at a time. And you can see that they start to line up. John Maloney put all this layout constraint stuff in our system, and in fact implemented most of the code for the user interface. Now I've got my buttons all lined up. This button here is kind of acting in a funny way. Well, with a core sampler, I can also adjust the layout behavior, and I could see on these buttons that I have a series of options. One of them is to be shrink wrapped. That causes the button to shrink down around its label there, nice and tightly. So I'm almost ready. I think I'll want to put this inside a frame object, and I'll resize this frame to be nice and big and drop the gas tank in here and this row and try to make a nearly completed application. Let's add a few atoms. Tell the row to horizontally fill the available space. And we'll also want to change the color of this object. We can make it some uniform hue. And there we are. We've finished a complete application. We could move this off into its own window if we want to. So everything was done very directly, had a very immediate feel, and without the run-edit distinction, the system kept running the whole time, gave it a very live feel. There's another way in which self-system is a lot like the real world. There's a lot more to it, the screen, than you can see at any one time. To see it all, we're going to use this radar view object. In the radar view, we can see the bounds of our own screen here, and that there are other objects off to the side. We go over there to visit them, or back. And we can see a small rectangle up here with objects moving around. That's because Mario's been very patiently waiting this whole time. He's another user on the network in this very same large space. So let's go visit Mario. I'm moving up here. Before we visit Mario, let's look at this application. This is a self web browser. and it's looking at the self home page here. But because it's built out of self objects, we could take it apart and use images from across the web and so on, embedding them in our own objects however we want. Okay, so now we're finally ready to go visit Mario. And let's come up here to the side. So, Mario, can you hear me okay?
Yes, I can hear you loud and clear.
Why don't you tell us about this, looks like Smalltalk stuff you're doing?
What you see on the screen is a Smalltalk implementation constructed entirely in Self. It shows that a prototype-based language is capable of emulating all the features of a class-based language. For example, the Self objects in this system are used to emulate Smalltalk classes. Second, it showcases Self's implementation technology. This implementation of Smalltalk is at least as fast and occasionally 3 times as fast as the best commercial Smalltalk implementation. As you can see, the Smalltalk utilities on the screen are all built using Self's direct manipulation facilities. Randy, what are you doing there?
Well, I've essentially made a class browser by ripping out the first couple panes of the browser, and you can see things still work down here.
And that's it.
Well, we've seen the language semantics and the user interface of Self, but there's been a hidden third player at play all along in the system. That's the implementation. I've got Dave Ungar here with me, and Dave and I designed this language many years ago, but Dave's been the guiding force getting it implemented, him and some very clever graduate students. Dave, can you tell us about the implementation a bit?
Sure, Andy. Most compilers are there to translate your program, and you see them do it, and then you run it. But just as in the real world, you're not aware of the physics going on that makes this table seem solid, so we've made our implementation invisible. It's more like a magician to try and convince you that these objects are real, even though it's doing a lot of tricks behind the scenes to get that effect. And in order to do that, we have to have it work fast enough so that you're not actually aware that it's stealing time from your tasks to do its job. So we use several compilers, one that's fast but not very good, and another one that's good but not very fast, that's used selectively only when needed, to get both the computational speed but also to keep the compilation time out of your hair. We also use a lot of tricks so that when you go to debug your code, the optimizations are automatically undone, so you never actually see that they've happened.
Yeah, that compiler is doing an awful lot of work. You and I have talked about trying to create a unified experience with this threefold effort: the language semantics, the user interface, and the implementation.
Yes. As we've talked about object-oriented programming, I think we're coming to the understanding that the programming part may only be a transitional phase from procedural programming to object-oriented programming to interacting with objects. So that instead of spending a lot of time telling objects what to do, you just bang on the objects and they bang back or do whatever they're going to do for you. So that the feeling is more of being immersed in a world of objects responding right away and giving you the ability to change what they do, rather than a more classical programming metaphor where you spend a lot of time talking to the computer before it actually does something for you.
So the self, language, user interface, and even the implementation play a role in creating an overall experience of a system based on principles borrowed from the physical world. But if we took the physical world metaphor seriously, wouldn't we create something like this, an immersive environment with objects I could rest my foot on, for example? Well, we're saying that perhaps you don't have to go that far. By concentrating on the maybe more important principles of directness, uniformity, and modelessness, you can create a system that captures a lot of the comprehensibility and coherence of the physical world. And we humans are pretty good about forgiving for inaccuracies in our metaphors. After all, these objects aren't really here with me. And in fact, you're not actually watching me, it's just a videotape. And after all, if we were to literally replicate the physical world in the computer, we would be unable to transcend the physical world's limitations. Thanks for watching.